You guys loved the last Avatar video on how space travel works, but what if I told you that once humans arrive on Pandora, spacecraft stop being the most interesting machines in the story? Instead, it's actually the ground equipment that stands out. Specifically, the human-operated robotic suits used by the RDA, the AMP suit, the Skel suit, and the crab suit. Each one is designed for a very different environment, and each one solves a specific mechanical problem. They're so darn cool. But what if I told you that they're actually based on real-life giant robot suits? 18 feet tall with a blade that we almost got built and used around America decades ago. In this video, we're going to break down how of these suits actually works, the AMP suit's control and weapons, why the Skel suit trades protection for mobility, how the crab suit adapts to the same principles underwater, and why machines like this might just be impossible in the real world. Let's start with the largest and most heavily armed, the AMP suit. The AMP suit, or the Amplified Mobility Platform, is the largest and most complex of the robotic systems used by the RDA. Despite its size, it's not an autonomous robot, it's a human-operated mechanical frame designed to scale human movement up rather than replace it. The operator sits inside of a sealed cockpit positioned within the torso of the machine. It's a little bit goofy looking, but from there the suit mirrors the operator's arm movements directly with force feedback transmitting resistance back through the controls, so they can feel it when they move their arms around. This allows the pilot to retain human dexterity while applying far greater strength. But the lower body works differently, because an 18-foot tall machine cannot safely mirror a human stride. The operator provides directional and force inputs through foot controls, whilst the onboard systems handle balance, step placement, and momentum. The result is a system where the human supplies intent and the machine executes movement, which is kind of similar to how our brain works. We think we want to walk over there, and our legs carry us there. Think about it like that. And this separation is what allows the AMP suit to walk, stop, and turn on uneven terrain without constant operator correction. Although it also introduces constraints that aren't immediately obvious. The cockpit itself is sealed and pressurized, allowing the suit to operate in toxic or hostile environments without the need for, say, a jumpsuit like you would have on a fighter pilot or something like that. The pilot can wave around, they can communicate, they can access other machinery inside without the heavy breathing apparatus. Visibility is provided through a transparent canopy, and in the event that that canopy is compromised, say with bow and arrows, it can be jettisoned entirely. The operator then relies on an external breathing system, allowing limited continued operation outside of the sealed cab. He grabs a mask in the first movie and fits it over his face to keep operating. In practical use, the AMP suit is a multi-role platform. Its hands are capable of manipulating tools, lifting cargo, and performing construction tasks, but the same structure allows it to carry heavy weapons that would be impractical for infantry to deploy on foot. These include large caliber autocannons, grenade launchers, and close combat equipment such as an oversized combat knife scaled to the suit's reach and strength. And this makes a lot of sense when the local inhabitants of the moon of Pandora are significantly taller than a human and significantly can shrug off human-based ammunition. So you need a big gun that can actually shoot and pierce their skin, and to hold such a big gun, you need a big suit of armor. This combination of dexterity and firepower explains why the AMP suit looks less like a traditional vehicle and more like a scaled-up human. It's not designed purely for speed, armor, or firepower. It's designed to do what an infantry soldier does while carrying heavier loads and operating in harsher environments at a much larger scale. Those choices come with trade-offs, however, especially around concealment, stability, and complexity of keeping a tall machine upright under load. But I'll talk all about those big flaws at the end of the video, because we can cover all three then. Well, what if I told you that this design philosophy is not fictional? A machine using almost this exact control logic, direct human mirroring, force feedback, and intentional base leg control, was actually built and tested in the United States more than half a century ago. That's right, to understand where the AMP suit really comes from in the world of Avatar, we need to step out of Pandora and into the Cold War America to a series of experimental machines developed by General Electric. Because long before Avatar imagined AMP suits, engineers were already trying to build it for real. Beginning in the late 1950s, General Electric was contracted by the US military and the nuclear industry to solve a practical problem: how to allow humans to handle radioactive materials without exposing them directly. The approach GE pursued was not automation, but mechanical replication. That's a tricky one, folks. Mechanical replication. Instead of programming machines to act independently, engineers built systems that directly mirrored human movement. These became known as master-slave manipulators. An operator wore a mechanical control harness, and a much larger machine duplicated their arm and hand movements in real time. The most advanced of these systems were developed under engineer Ralph Mosher. Mosher's early machines demonstrated precise force feedback. When the manipulator encountered resistance, that resistance was transmitted back to the operator, and this allowed heavy or dangerous objects to be handled by feel alone, without relying on cameras or automated control logic. You didn't have to look into a screen to see what you were doing, you were getting force feedback through the controls. And these systems proved remarkably capable. Operators could perform delicate tasks such as rotating rings or aligning components, while also lifting and crushing loads many times heavier than a human could manage unassisted. However, these systems were fixed installations. They couldn't move. So GE's next step was to make this technology portable. This led to Hardy-Man, the first serious attempt to make a powered exoskeleton. Hardy-Man was designed to allow a human operator to lift loads of up to 1,500 pounds while feeling only a fraction of the weight. But in practice, the Hardy-Man system was unworkable. It weighed over a ton, relied on external power, and suffered from severe control instability. Even minor faults caused violent movements, making it unsafe to operate. The exoskeleton concept was abandoned before it could ever be demonstrated outside of controlled conditions. So rather than scale the machine down to try and make it work, GE scaled it up. If a human could not safely wear the machine would have to safely wear the human instead, or rather carry the human inside. And this resulted in the Pedipulator, a full-scale walking vehicle developed in the early 1960s. It featured two telescoping legs, approximately 12 feet tall, long articulated arms, and a control cabin in which the operator stood fully strapped in, like I'm standing right now. And this machine was capable of lifting loads exceeding 8,000 pounds and was designed to traverse rough terrain, step over fallen trees, and maneuver through dense vegetation. And control sensitivity was high enough that it could either push a loaded vehicle through mud or perform very light contact without damage. It was also fitted with different end effectors, including a cutting tool designed for the forestry industry, but also kind of looks like a combat knife. Notably, the Pedipulator balanced without electronic computers. The operator stood on a platform that rocked naturally as their weight shifted, and that motion was mechanically translated into leg movement, allowing the machine to balance using the same instinctive corrections as a human body. It had no sensors, it had no software, and it had no automation. And it looked just like the AMP suits from Avatar. Despite successful demonstrations, the Pedipulator revealed significant limitations. The fuel consumption was extremely high, it exceeded that of contemporary armored vehicles, and the hydraulic systems required for precise control were vulnerable to dirt, moisture, and shock, making field use unreliable. Plus, the height of the machine raised its center of gravity, increasing the risk of instability, and operation was physically demanding, with operators experiencing fatigue after short periods of use. It wasn't easy or fun to use. GE attempted to address these issues with later designs, most notably with something called the walking truck. This machine reduced the height, increased the stability by adding additional legs, and improved terrain handling. However, it introduced new problems, included limited endurance, high hydraulic fluid requirements, and a steep training curve. Only a single prototype was ever built, and it never left the laboratory. Although I can't help but think that this design looks a lot like those robotic dogs that we're now seeing everywhere. So I wonder if that technology could come back, but I'm getting ahead of myself. None of these machines would ever enter service, and they weren't abandoned because they failed to function, but because the surrounding technology couldn't support them. Power systems are heavy and inefficient, and sensors are primitive. Real-time balance control relied entirely on the human operator, and these problems are also implicitly present in the AMP suit's design in Avatar, but the difference is that Avatar assumes that these constraints have been solved, and we actually see that in the second movie with a new type of robotic suit, the Skel. The Skel suit represents a deliberate shift away from the AMP philosophy. Where the AMP suit scales up a human into a vehicle-sized platform, the Skel suit stays much closer to the human body. Officially designated as the EXO-32 Light Mobility Platform, it functions as a powered exoskeleton rather than a fully enclosed machine. The operator remains largely exposed, and there's no cockpit, there's no sealed environment, and very little armor. Instead, the Skel suit focuses on one thing: mobility. The frame extends the operator's legs, increasing the stride length and step height, while powered joints amplify leg strength. This allows a human to move through the dense terrain faster, step over obstacles, and maintain pace in environments where wheeled or tracked vehicles would be ineffective, like the jungles of Pandora. And unlike the AMP suit, the Skel suit does not rely on direct mirroring of large limb motion. The operator's legs remain inside a constrained space, so the suit interprets pressure and direction through foot sensors rather than copying full leg movement. Onboard systems translate those inputs into stable steps, adjusting for uneven ground and obstacles automatically. This makes the Skel suit easier to operate and less physically demanding than earlier walking machines. It also makes it safer to use around other humans. Because the Skel suit is lighter and much less powerful than the AMP, although you can still use it to beat up the natives, its movements are intentionally limited. Collision avoidance systems prevent the long legs from striking nearby personnel, and the reduced mass lowers the risk of catastrophic injury if the suit falls or if it's disabled. And from a tactical standpoint, this explains why the Skel suit looks unprotected. It's not designed to absorb heavy fire, it's designed to go where infantry can go and keep up with them. The suit raises the operator roughly to the Navi height, allowing the soldiers to move, see, and fight on more equal physical terms in close terrain. The weapon systems are adapted also accordingly. Traditional rifle stocks are removed, and aiming is handled through camera-based sights linked to the operator's HUD, compensating for the altered arm geometry. And the recoil is absorbed by the exoskeleton rather than the operator's body, allowing more accurate fire even from unconventional shooting positions. You just know that the US military would love these right now. In effect, the Skel suit does not replace infantry, it stretches them out. And compared to the AMP suit, this is a much more conservative design, but a more realistic one. Lighter systems focused on endurance and access are often more practical than heavier armored walking platforms. But now, of course, it's time for my favorite suit from the Avatar universe. The crab suit takes the same human-in-the-loop control philosophy seen in the AMP and Skel suits and adapts it to an environment where walking is no longer the default option. Officially designated as the SMP-2 crab suit, the human-operated submersible is designed for underwater work, recovery, and security operations. Unlike the AMP and Skel suits, which are optimized for forward movement, the crab suit is optimized for stability and positional control. The pilot sits inside a sealed, pressure-rated cabin constructed from light composite materials. This cabin functions as both a cockpit and life support system, allowing the suit to operate at depths of up to 500 meters. The structure prioritizes pressure, resistance, and durability over visibility, reflecting its role as a working vehicle rather than a combat platform. Extending from the central cabin are 2 manipulator arms and 4 articulated legs. It's a crab, essentially. Now, these arms actually use the same direct human control and force feedback principles as the AMP suit, allowing the operator to perform precise tasks such as lifting, cutting, and attaching cables, or handling irregular objects. This makes the crab suit suitable for underwater construction, salvage, and recovery work that would be difficult or impossible for traditional remotely operated vehicles or people in scuba suits. The legs are also where the design becomes fundamentally different. Rather than using long strides, the crab suit relies on a wide, low stance to maintain balance. The four-legged configuration distributes weight across multiple contact points, significantly lowering the center of gravity and giving it much more grip. And this is critical underwater, where the currents and uneven terrain constantly destabilize tall, narrow machines. The feet are also semi-prehensile, allowing the suit to grip rocks, seabed structures, or vegetation. This allows the operator to anchor the vehicle in place, resisting currents whilst performing fine manipulation tasks. And locomotion is hybrid. On a solid surface, the crab suit can walk slowly using its legs, and in open water, the big integrated thrusters provide propulsion, allowing the suit to hover, reposition, or transition between locations without relying on continuous contact with the seabed. This avoids one of the major limitations of walking machines underwater, the inefficiency of stepping when buoyancy and drag dominate movement. And when it comes to operating the legs, the operator provides directional and force inputs, whilst the onboard systems coordinate limb movement, balance, and resistance. This allows the pilot to focus on task execution rather than constant stabilization, which is essential in low visibility environments where visual reference points are limited. And although the crab suit can be armed in the Avatar universe, its design clearly prioritizes utility over combat. And its strength lies in controlled movement, endurance, and precise interaction with their environment rather than speed or firepower. Taken together with the AMP and Skel suits, the crab suit completes the spectrum of Avatar's human-operated machines. Where the AMP suit emphasizes strength and the Skel suit emphasizes mobility, the crab suit emphasizes control. And I just love the triangle that forms. These designs still run into the same fundamental limits that have challenged real-world engineers for decades. The first is power. Walking machines are energetically expensive. Every step requires lifting mass, stabilizing balance, and correcting motion in real time. As size increases, power demands rise sharply. This places strict limits on endurance, speed, and operational time, especially for systems that must carry weapons, sensors, and life support equipment. The second is protection versus mobility. Effective armor is heavy. Adding meaningful protection to a human-sized or larger walking platform rapidly increases the mass, which in turn requires stronger articulators, reinforced legs to carry it, and, you guessed it, more power. At a certain point, the system becomes slower, more visible, and less agile than existing vehicles designed for the same role, like a tank. This trade-off is visible across all three designs. We see that the AMP suit sacrifices concealment and agility for strength and utility, and the Skel suit sacrifices protection for speed and access. And then lastly, the crab suit sacrifices speed for stability and control, and none of them can fully escape the balance between that weight, mobility, and survivability. And that leads very nicely into the third limitation, which is visibility and exposure. Tall walking platforms struggle to use cover effectively. Their height makes them easy to spot, and their silhouette limits concealment in open terrain. Even lighter systems remain vulnerable to ranged weapons, environmental hazards, and concentrated fire. And this isn't a storytelling flaw, it's a geometric one. Like, for example, we live in a world where a drone can take out a tank. And if you had a giant walking robot coming through the battlefield that's so heavy and slow and exposed and can't hide behind anything, and a drone can just take it out, you've got to start to wonder, like, why didn't we just use a tank in the first place? Walking robots don't necessarily have any advantages, apart from maybe navigating the complex environment of the jungles of Pandora, than tanks that we have in our own world. But I'm not done yet. A fourth flaw is complexity. Human-operated walking machines rely on a tight feedback loop between operator mechanics and control systems. As complexity increases, so does the maintenance burden, training time, and failure risk. Hydraulic systems, articulators, sensors, and joints all introduce points of vulnerability, particularly in harsh environments, like the jungle moon of Pandora. And historically, these factors have favored simple solutions. Wheeled and tracked vehicles are more efficient at carrying armor and firepower, and aircraft are more effective at rapid force projection and speed, and conventional infantry remains the most adaptable in complex terrain than large mechanical systems. What we have today works better than these robots. And this is why powered exoskeletons and walking vehicles have repeatedly struggled to move beyond niche roles. Avatar assumes that many of these constraints have been particularly solved, that advanced power sources, improved materials, and highly capable control systems allow these machines to operate more effectively than their real-world predecessors. Even so, the underlying trade-offs remain. These machines are not miracle weapons, they're specialized tools, and when viewed through that lens as utility platforms adapted for combat rather than purpose-built war machines, their designs make far more sense. In the end, Avatar's robot suits are not unrealistic because they acknowledge engineering limits, they're interesting because they acknowledge them, and they ask what might happen if technology finally caught up. But of course, whether or not that future arrives in our world is an open question. But the problems standing in the way are the same ones that engineers have been wrestling with for more than half a century. And for now, physics is still undefeated. I'm filming this on the last day of the year of 2025. So if you're watching this in 2025, Happy New Year. And if you're watching this in 2026, Happy New Year. It's a new year, so I hope you have a great one.